And we are now recording. All right. So basically, if anybody else joins, great. But otherwise, please feel free to ask me questions as I go along in this kind of basic presentation. I've tried to, I've done most of the first parts of the project, so I've kind of tried to tailor this stuff to kind of some things about C that I think that you would expect to understand in order to understand how to attempt the problem without getting into any of the specifics of the problem, obviously. So, so this is a review for programmers who've not seen C or had a minimal exposure to it. And this is meant to introduce you to the language. It's not meant to in any way, shape, or form be comprehensive. If you want something comprehensive, I have a book at the end that you probably want to get that'll, really dive into everything deeply. There are some distinctions between C I'd like to make in comparison to other languages. And so that this is like, say, like Python or JavaScript, the code is compiled rather than being interpreted. Unlike Java or C#, the code is compiled to machine instructions rather than bytecode. So typically in Java and C#, the code's converted into a machine portable representation, and that machine portable representation is ran unless you get into some situation where the code needs to be converted into machine code, and even then only a minimal amount of that code is converted into machine code. What this really means, the biggest kind of thrust of this that may be different for you is that it means that every time you make a change to the code, you have to recompile it. You can't just change the C module and then run the executable expecting it to run. You have to recompile it. In this class, we provide the TAs and the instructors have provided something known as makefiles for you. To change the code, you just simply need to change the files, then bring up a terminal and then type in the command make, and that will automatically make the code for you. It will print out errors if there are errors in your build process that you need to resolve. You have to resolve all of the build errors before you can successfully run the code. That's a very big point as well. You cannot run a partially errored code, unlike other languages where you could, especially interpreted languages. You can run an application like the Echo client as just saying /echo client when you're in the location in Linux. One thing I'd really like to say about C that's different than a lot of languages is it provides very little to no protection. The TAs have turned on some of the protection like stack guarding, memory guarding, things like that. But in the end, C does exactly what you tell it to do. And it will do things like it will let you read past the end of an array. And since there's memory past the end of an array, it will let you do that. The only problem is that the results are probably undefined and undesirable. So, there a lot of the protections that you may be used to as a programmer have been removed in the language of C. And I definitely want to stress that, because if you're expecting the programming environment to prevent you from doing certain things, it won't. It'll let you do them, and it will have a result. That result may or may not be what you're expecting. So here's kind of a structure, probably the quintessential simplest program on the planet Earth that everybody goes over, just to give you kind of a basic broad overview of it. So it's a .c file, so you name it whatever you want, but the extension will be .c. The first thing is that there's this pound include. Effectively, what pound include does is it's almost the same as a copy and paste into your code. It's not like an import directive or something like that. Whatever C code is inside that header file is basically ran. But for the most part, it's used like imports. So when you say pound include studio.h, or which stands for standard IO.h, you're bringing in the standard IO functions. In this case, printf is one of those standard IO functions which will print data to the screen. So that's what that does. The next piece of this is the entry point. So in every C program there is one entry point, and it's called main. You can optionally add some arguments to main, which I won't go over in lecture to actually allow you to read the command line, but we're not going to do that. So this is just an entry point that takes no command line parameters. We'll go over what scope is, but when you start the function, you have to start a scope. And then we're going to go ahead and call a function. In this case, we're going to go ahead and say printf hello world with a new line character. And then we're going to return a value. The main function, some operating systems will allow you to return nothing from main, but some operating systems require you to, depends on the compiler and the operating system you're on. But they all allow you to return a value. So portable code will return a value. And then this, whatever value you return from here, you can actually inspect in your shell. So if you're writing a shell script or something like that and it fails, you can actually look at this return code to determine whether or not it failed or not. So we'll just talk a little bit about comments real quickly. C supports two styles of comments. It supports both a single line comment, which is a double slash, and a multi-line comment, which starts with /* and then ends with a */. There's no standard about whether or not the */ style can be nested, so watch out for that. Basic mathematical operators that are supported, as you would expect. It supports addition, subtraction, multiplication, division. It supports integer modulo division. It supports it in the signed form as well as the unsigned form, depending on what you do. When I say signed form, what I mean by this is that mathematically a modulo is defined. If you take like -1 modulo 5, mathematically that should be 4, but C++ will return -1. So that's just what I mean by the signed form of modulo. Supports standard relational operators, supports logical operators, logical and, or, not. It supports bitwise operators, a bitwise and, bitwise or, bitwise or, shift to the left, shift to the right operators. It also supports this +, minus, which is a shorthand way of saying value +1, value -1, and then store it to itself. So if you say x ++, it'd be the same thing as saying x equals x + 1. But there are two forms of this, the postfix and the prefix variant. The postfix variant, the increment runs after the line of code, and in the prefix variant, it runs before it. There's also a lot of these operators you can combine with the assignment operator, so you can say, for example, plus equals, minus equals, star equals, divide equals is just a shorthand alternative. And please stop me if you have any questions.
Yeah, so you're saying that there are no logical operators like and or, so
there
just
are.
to clarify. Okay, so in if statement we would use just single and or
No,
yeah?
you would use the double and the double or, which are these operators right here in an if statement. If you wanted to say if x equals 0 and y equals 0, you'd say if x equals 0 and y equals 0, because the double equals test for equivalency, whereas single equals test for assignment, which that can throw some people off who are used to a language where a single equals and an if is test. In C++, if you say if x equals 5, you're actually assigning the value of 5 to x and then testing around 5. Does that make sense?
Yep.
So watch out for that if you're from a language where if you say if x equals 5 with a single equals means test, because it does not mean that in C++.
I'm from Python world, so I should be fine.
Yeah, no. Python's got some differences, but languages. Once you go through enough languages, you learn that they all borrow from each other,
yep.
and they're all different, and so it's interesting. But yes, so these are the operators you'd want to use inside of an if statement: the and, or, not. Whereas the bitwise and, the single and, what that's going to do is it's going to take all, like if you look at all the ones and zeros in a value and all the ones and the zeros in a value, it's going to do the bitwise operation of all those ones and zeros, which is probably not what you want inside of an if statement. Sometimes it is, but usually it's not.
I also have a question. Every once in a while, I see people doing bitwise shift, bit shift to the left or to the right. So
Yeah.
like when they want to like divide by power of 2, does it really make sense, or
Well, I mean,
compiler is smart enough to figure it out that we
so
can
yes,
optimize this?
you're hitting the nail on the head. Is that mathematically they're the same expression. However, most modern compilers, like back in the maybe the late 70s, early 80s, compilers may not have been intelligent to figure that out. But I would say even by like the mid 80s, compilers were smart enough to figure that out. There's a lot of things that compilers still aren't smart enough to figure out on their own. This isn't one of them. And so I am kind of with you in the sense of like I would prefer code clarity over complexity. And so therefore I would just keep the divide by 2 or the multiply by 4 instead of a shift by 1 or a shift by 2 respectively.
Okay.
Let's see here. So one of the so you don't remember Python background. One of the major differences between C and say a language like Python is that C is what we call an explicitly typed language, and this means that when you create a variable, you not only have to create that variable, but you have to say what that variable is in terms of its type. And once you create that variable, as long as it's in a current scope, and we'll go over what scope means in a bit, but as long as that variable is in scope, it can't change types. It's immutable in terms of type. So there's some basic types of char, short, int, long, float, double, long, double. They're signed by default. I should change that. But you can add the unsigned keyword to any of these to make them unsigned. So you can say unsigned char, unsigned short, unsigned int, unsigned long. The unsigned modifier does not have any meaning on any of the real number types, float, double, and long, double. Now, this is the next thing I really want to say, is that in C, there's no hard and fast rule about the size of any of these data types. The only thing the standard sets is that the size of a char must be less than or equal to the size of a short, must be less than or equal to the size of an int, must be less than or equal to the size of a long, and similarly for the real types. Now, in practice, this is what you run into for the most part. In practice, you run into char is an 8-bit signed value, short is 16-bit signed value, int is a 32-bit signed value, float is 32 bits, and double is 64 bits. For the other types that I talked about, going from compiler to compiler or operating system to operating system, there's still a lot of disagreement about what the sizes of these various things should be. If you don't like the fact that there's ambiguity in these sizes, and I definitely do not like the fact that there's ambiguity in these sizes, there's a header file and some additional types defined in this header file called std_init.h that define additional types like int8_t, and int8_t is guaranteed to always be 8 bits under all circumstances and signed. uint8_t is guaranteed to be 8 bits unsigned on all platforms. So that's useful if you're worried, if you don't like this idea of you're not always sure what you're getting in terms of these data sizes. But like I said, you can be relatively confident that these rules hold pretty. I have not run into a compiler in a long time that does not obey these rules. Let's just put it that way. When a variable is declared, its memory is uninitialized. I can't remember if that's true in Python or not, but in C it most certainly is. So if you say int x and then immediately print that x, and you run an application multiple times, you may actually find that every time you run the application, it will print a different number. Okay? So you definitely want to make sure that you always initialize your data to something, or that you don't care that it's uninitialized somehow. Sometimes that does come up. But the key point I want to make is that you cannot rely on the fact that the compiler is going to say 0 initialize everything. It's not going to do it. The other thing is that there's a size of operator. This operator is very important in the C world. You'll find utility for it in the assignments, I guarantee it. I won't tell you how, but I'll just guarantee you that you'll need it, is that what it does is it tells you how big in bytes, not in bits, but in bytes, either a type or a variable is. So if you say size of int, on most computers it will return a 4. But if you said int x and then said size of x, that's valid too, and it will also return a 4. Okay?
Can we, when we do size of, we can do it for both types and for variables as well?
And for members of structures, which we'll get to later. So if you have a structure and you name the structure, and you have an instance of the structure called Bob, and there's a variable in there called hat. So you could say size of Bob.hat, and then it will tell you the size of that member inside the structure, or you could also say size of Bob, and it will tell you how big the structure is. Okay?
Nope. Okay.
In bytes. And all this is in bytes.
Got it. One additional question. I don't see a Boolean on this slide. Don't we have Boolean in C?
So if I remember correctly, C11 might have introduced Boolean. C99, which this course uses as its compiler, does not support Boolean in the language spec. C++ does. So for Boolean, what you're going to want to do is you're definitely going to want to treat int as your Boolean type. I would definitely recommend that. And then just, 0 is your false case and 1 is your true case. You can do what say Windows did and go ahead and do a pound define or create a global variable called true and false. Probably a pound define is better just in the sense you can't change it. I didn't go over pound defines in these slides, but it's kind of a way to make a replacement alias. So like you say pound define true 1, every time it sees true, it would be as if you wrote the number 1. And in this case, I would recommend that true be all caps,
And
like in Windows.
do people do that all the time, or?
Well, like I said, Windows, like if you pound include windows.h on Windows, you will get true and false defined 0. Mostly exactly for this reason that on C, there is no such thing as Boolean. In C++ there is. There is a reserved data type called bool and a little true and a little false. And there's very explicit reasons why they added that to the language rather than not. But in C, you don't have it. And like I said, they added it in C11. But if I remember correctly, it's in C11 and not in C99. So,
okay.
And just like C99 and C11, those are the years that the spec was adopted. So C99 was adopted in 1999, and C11 was adopted in 2011. Okay?
Mm-hmm.
All right. So an array. So an array is basically just a set of a certain type. So I'm going to get to pointers in a little bit, but I do want to say that arrays and pointers are not the same thing. A pointer points to a piece of data in memory, whereas an array declares a piece of memory of a given length. Okay? This has many impacts. For example, if you use the size of operator on something that's an array, you'll get the size of the entire array, whatever it is, okay? So, if it's this big, you'll get it, make it bigger, it'll be bigger, whatever. Whereas if you do a size of a pointer, which we'll get to later, no matter how big the thing is that the pointer's pointing to, it'll always be the size of a pointer. So, and just so you know, on a 32-bit operating system, a pointer is 32 bits. And on a 64-bit operating system, a pointer is 64 bits. When we're talking about the size of the operating system, that is the size of the pointer that the CPU uses. Okay?
Mm-hmm.
Which directly affects how much available memory you have. Okay, so if you want to make an array of size of 5, this is basically how you would do it. You'd say int x angle square bracket 5 square bracket, and that will make an array of size of 5. Again, the data inside that array is completely uninitialized, so it's just random garbage, and every run it will be something different. Now, if you can initialize the data when you create an array, as I'm showing here below. Also, when you do it this way, you can actually not include the size as well. you can omit the size inside the bracket, and the compiler will infer from the number of elements that you provide how big the object is. Okay.
Mm-hmm.
All right. So talk a little about strings in C++. Strings in C++ are curious little things. Technically, a string is simply an array of type char. We talked about what type char was earlier, but that's all it is. It's an array of type char. But there's an interesting caveat here. If I was to print the size of hello, the string that just contains hello, it returns 6 and not 5. There's only 5 characters in the word hello, but it returns 6. Why did it return 6? Well, the reason why it returns 6 is by definition, in C, all strings have an additional character appended to the end of a string. It's the hex character 00, and it means that the string is null terminated. This is how you know where the end of a string is. So this is unlike some other languages that internally will store the size of the string and then the data of the string. There is no size anywhere stored of the string. Rather, there's just the end marker of the string, and you actually have to use a function, which I'll tell you what that function is at the end, to actually know how long that string is in bytes. Does that make sense?
Yep, I discovered it a couple of days ago. So.
Yep. Okay.
I'm sorry. Can I have a question?
Absolutely.
I'm not sure if you gonna cover it later or not. So, for me, coming from Python world where we have arrays of the size which we don't know, how would we approach the same kind of problem? Or
so in this case here, it is a little unclear what the size of this object is, right? This x, right? Like it's definitely not explicitly stated here. What you can do is you can say size of x, and what it will divided by the size of int. Okay. Mm-hmm. So the size of x will be the size of the entire thing. Now the x array is tightly packed, which means that each integer, there's no blank space between it. It's just int in memory. So if you say the size of x over the size of an int, it will return you 3 in this case. If I added more values, it will return the size of that array. So that mathematical operation, size of the array over the size of the underlying object, will work. However, this will not work for pointers. I want to be very clear about that. And you cannot pass an array to a function, okay? You can only pass pointers to a function. You may deceive yourself into thinking that you can pass an array into a function because you can say int x bracket bracket in a function, but size of breaks when you do that. And so typically what you have to do with a function, if you want to pass an array into a function, is you have to pass 2 things into the function. You have to pass the size of the array and the pointer to the array. Does that make sense?
Not really.
So what you're getting at is absolutely correct. In Python, you can ask an array what its length is. There's not really a way to do that. So you have to know through some other means what the size of the array is and keep that around effectively. Okay?
Okay.
You have to keep it around as extra bookkeeping effectively.
Okay. So imagine that I have an array that is growing over time. Okay, so like, I don't know, you're doing some filtering or whatever, you have an array that you fill up with data.
Right.
How do you approach this kind of
we'll get into memory management here in a little bit, because that is its own memory management is a lot more explicit as well, unlike Python, where it handles this all for you. What you're going to learn is that C, you tell it everything to do, almost, pretty much, and it doesn't do anything for you. And that's both a good thing and a bad thing. It's a good thing in the sense that you have a lot more control. And then when we're dealing with stuff like on the operating system level, we need control. But it also is a bad thing because it's really easy, as one of the authors of the C language said, it's very easy to shoot yourself in the foot. That's a quote. That's a big problem. It also means you're going to end up writing a lot more code to do the same thing. Your code's going to run faster, but you're going to end up writing a lot more of it. Okay?
Mm-hmm.
All right. So, it's
okay, Chris, I'm sorry to interrupt you.
Go ahead.
It seems that we have a wrong link in the Slack. So I just pasted the link of this meeting, and maybe somebody will actually join. Sorry for that.
No, that's perfectly fine. I didn't even notice that myself. Okay. Well, I'll keep that up. Okay. So if statements are also if statements are pretty much what you would expect in most languages. Even say it's fairly similar to what Python is in terms of if statements as well. Basically, you'll say, int x equals 0. If x equals 5, I want to go ahead and do something. Now, one interesting thing about if statements in C is if you don't put a logical expression in there, such as, say, if you just say if x, then it's a shorthand way of saying if x is not equal to 0. If actually anything other than 0 in the universe, that if statement will evaluate to true. Otherwise, it will evaluate to false. Okay?
Okay, so if you have an array, right, regardless of what values this array has, we will always return true, right?
Well, if you just say, if x is an array, and you say if x, because effectively, there's this weird thing where arrays and pointers are the same thing, but they're not the same thing. If you say if x, it's going to treat that x as a pointer at that point, that it's pointing to some value in memory, or location in memory. That location is definitely not going to be location 0. So yeah, it's always going to be true. So you're going to want to say if x square bracket to square bracket. You're actually going to want to, individually test the members of the array manually. Like I said, arrays and pointers have this weird thing where they are the same thing, but they're not. All right. C also supports a single line if known as a ternary operator. You don't need to use the ternary operator if you don't want to, but I just include it here for completeness, so you can do a statement similar to this. And basically, what this will do is it will assign to the value y a 0 if x is 5, and it will assign a 1 in all other cases. So basically, this is the conditional. The first parameter is what you assign if it's true, and the second parameter is what you assign if it's false. Also, C supports an else statement that you can basically say if this thing, else this other thing, and you can chain them up. So you say if, else, space if. In Python, I think it was like elif, elif. You have to put them all together. In this case, it's else space if is what you're going to want to do in order to actually have a nice long chain. Speaking of nice long chains, there is another type of if control that's supported in C called a switch statement. I'll actually go over kind of what this code's doing later on, so I'm going to use it as an example of function pointers. But basically, what this does is it switches on a character C. In a switch statement, there's this reserved thing called default. Default basically is the thing that is taken under all cases that are not covered. And then these are the cases. one thing I forgot to mention in here is that there is a command called break. And what this does is this stops from processing the next case statement. So because you're returning out of this function in this particular example, you don't need a break because you're leaving the function entirely. But typically inside of the case statement, you'll need a break as well in order to avoid falling into the next case statement. Because by default, if you're not returning and you're not breaking, you will just fall into the next case statement. Does that make sense?
Yeah. So basically, we will have in machine code we will have a jump, right?
Yeah.
If you do break. Okay.
Yeah. If you break. If you don't, you won't have a jump, and then you just fall into the next case statement and do whatever logic's there. All right. So the for statement is very useful. Obviously, it's one of the most useful things to a programmer. So we really should talk about it. So, and I'm going to use the canonical FizzBuzz test question as an example for this to kind of even give some more concrete example of what some of these things that we've gone over do. So basically, the for statement has three groups that you always have to include, even if you're doing nothing in one of those groups. You can do nothing in one of those groups by just saying semicolon, semicolon, by basically just putting nothing inside of that group. But all three groups must be included in the for clause. So the first group of the for clause is the setup. It's basically whatever you want to have happen on the first iteration of the for loop. So, for example, setting the initial value of the for. The second one is the test for completion, and the test for completion will be ran on the first iteration of the for loop. So that will determine whether or not the for loop has completed or not. And then the last one is the operation at each iteration. So this will not be ran on the first run, but it will be ran on each subsequent run. Okay? So let's go through a very concrete example here. So basically what this will do is it'll loop from the value 1 to 100, including 100 because of the less than equals. Typically you'll see less than 100 in most coding examples, and what that means it would only loop from, say, like 1 to 99. So be very careful. Also, the C language, I forgot to say this earlier on, I probably actually should amend my notes here. C is what is referred to as a zero-indexed language, which means that the first, if you have an array or a pointer or something, the first value in that array or that pointer is at location 0, not at location 1. Hey, Alex. You can go ahead and add audio if you want to. But I can't hear you or anything, so I don't know if you can hear us. But I'm going to keep going. So basically this will loop from 1 to 100. And then because we've gone over some other things, I'll just kind of go over what this code does. If the code is either divisible by 3 or it's divisible by 5, it'll enter into this branch of code here. And then if it's divisible by 3, it'll print out fizz. If it's divisible by 5, it'll print out buzz. Otherwise, it'll print out just the number. And then it'll always print out a new line. And so basically what this code will do is it'll first print out the number 1, then it'll print out the number 2, then it'll print out just the number fizz, and then it'll print out the number 4, and then it'll print out the number 5, and it'll continue doing that. And then once it gets to the 15, which is divisible by both 3 and 5, it'll print out the word FizzBuzz, for example. So this actually is part of a standard programming test that people use to weed out people who can't program at all. And it's called the FizzBuzz test. It shows up a lot. So loops. Simple basic loop. It just loops while a condition is true. And it also can be used in the do while form. So you can say do, oops. Totally screwed that syntax up. So basically, this form will do the test on the first iteration and all subsequent iterations until it fails. This form will not do the test on the first iteration and then do it on all subsequent iterations until it fails. And it basically, the way that it's written is kind of gives you a hint, because basically what this do does is that at the end of the iteration in assembly code, it will do the test, and this one will do it at the beginning in assembly code. So Dimitri, you're asking a lot about memory management. How do you resize something as it grows and things like that? Now we're going to get into memory management, which is one of the really sticky subjects of C.
Perfect.
Yeah. So in a language like Python, which you're familiar with, you know, all the memory management's done for you. If you keep adding stuff to an array, for example, under the hood it's making the array bigger, and it's making it bigger in memory and bigger and bigger and bigger, and you're not worrying about anything. That's not true in C at all. When you go out and you allocate a piece of memory through the function malloc, which is typically the function you're going to want to use, malloc is short for memory allocation. This example here will allocate 20 times the size of an init. So we talked about the fact that the size of an init on most platforms today is 4, so it'll allocate 80 bytes of data. Okay, but it only allocates 80 bytes. It doesn't allocate any more. So you can start filling up these bytes, but what happens if you need more than 80 bytes? Well, what you're going to have to do is you're going to have to allocate a pointer that's even bigger. You're going to have to use a function like memcopy. So there's a function called memcopy, M-E-M-C-P-Y, that can copy data from one piece of pointer to another with a size in bytes. You'll have to copy that data over, then free the old one, and then continue writing into the new one. Does that make sense?
Yep.
Now, hopefully for this assignment, if you do it right, you don't have to do stuff like that, but that is an option to do. You know, but like I'm trying to say is that memory management basically becomes your full control. And also, there's no garbage collector. So what that means is that means that it's fully incumbent upon you to release the memory when you're done with it. And it's your responsibility. And if you don't release the memory and you're allocating long enough, eventually you'll crash the application because you ran out of memory on the host system, even though you may not be using some of it anymore. So I think that our TAs have been gracious enough to turn on some memory leak protection as well. I've noticed that, like, if I accidentally leak a piece of memory when my application exits, it will actually say, hey, you forgot to free that. So that's really nice of the TAs. It's not something that's typically on by default in C. You have to explicitly go and turn it on. So that's awesome. Okay, so let's talk a little bit about.
Sorry,
go right ahead.
Back. Yep. So I don't understand why after freeing you still need to assign it to null.
You don't
Could
have
you please
to.
explain? Okay.
You do not have to, but I highly, highly, highly recommend it. Let me explain to you why I highly recommend it. So in C, everything's just memory. So I have a pointer here. When I say free, the pointer sum ints in this particular case is still pointing to the piece of memory that data used to exist at. No longer, the data I want is no longer there, but it's still pointing to it. So if I forget that happened, which in a very large code base can happen very easily, then you can accidentally try to access that memory again. It's called a dangling pointer, is typically what we call this type of bug in C, is a dangling pointer bug. And so that's why I just highly recommend that you assign it to null when you're done, so that if you try to access that memory again, you'll crash immediately. As opposed to one of the biggest dangers of a dangling pointer bug or a memory overwrite bug, which memory overwrite bug is, let's say you allocated 20 ints and you wrote to the 21st int. That would be an overwrite bug. So you
You can't track it anymore, right?
Yeah, you've gone off into la la land and you've done evil things. And so by setting it to null, well, that's a protected page by the operating system. I'm sure Ada will go over that later on about how you can protect different pages in memory space. That page is protected. So anytime you try to write to byte 0, the operating system goes, you can't do that. That's bad juju. So that's why, like, all pointers that don't point to anything should be assigned to null, so that you can never, under any circumstances, try to accidentally write to random memory. Because by and far, I will tell you from personal experience, I've been programming in C++ for 25 years. The worst type of bugs to deal with are memory overwrite bugs, dangling pointer bugs, and thread concurrency bugs. Those 3 bugs will give you the nightmares. Those 3 bugs are the type of bugs where you'll have one line of code that's the problem, and you'll spend 2 weeks looking for it. I've been there. I've done it. It sucks. So having good coding standards in place to prevent you from making those kinds of mistakes so that you don't have to spend 2 weeks in these debugging sessions is very useful.
Okay. I still have a question on this
No,
slide.
keep going.
So when we go into that example with int asterisk some ints, so could you please explain why on the right side we have int star there before the malloc?
Okay, so malloc returns a void pointer, and my pointer slide got after this slide, which I need to move that because I should have covered pointers before here. But I forgot to cover void star. So with void star, it basically says point to an untyped type. So I need to change that to an int star. So if you think about it from, are you familiar with object-oriented programming?
Yep.
Okay. So if you think about it from object-oriented programming, a void pointer, all pointers derive from the void pointer. An int pointer derives from it. A char pointer derives from it. So I can convert an int star to a void star without a cast. But especially in C++, and I think C requires you to do this as well, you have to have a cast to go the other way. Okay? Because now you're going from the parent class to the child class, effectively. I'm using an object-oriented metaphor to explain what's going on here, but it's the same general concept.
So if we will not do it, it will not be a valid C expression, right?
Yeah, I think, like I said, I know in C++ you absolutely must include this, or the compiler will fail. It will literally say, error, I cannot convert a void star into an int star. I can't remember if C is that strict. At one point in time it wasn't, but I think its strictness has gone up over time, and now it is so strict that it is required. But I would say, just as even if it's not required, I'd say it's a judicious thing to do.
Mm-hmm. So just to make sure I understood 100% this example, so here we are trying to say, okay, so take the size of int, which is 4 bytes, right?
Yes.
And multiply it by 20, so we have 80, which represent bytes, so we allocate 80 bytes.
Yes.
Then you say this is not pointer to something, this is pointer to int values, right?
Yes.
Okay, and then on the left side you're saying that we will have pointer which will point to the integers and the first memory address of this 80 bytes, right?
Yes.
Okay.
Yes, and that is a very astute point. That what this thing returns is the memory address, the first memory address of the 80 bytes that you've returned. You know, because you can make a pointer to anything inside that 80 bytes, but the thing that it returns is the very first thing.
Okay, and one more question. So do we have a protection that when we run the program, let's say in Linux kernel, do we have protection that one process cannot write to the memory assigned to another process?
In Linux, absolutely. Absolutely. And this function, I forgot to mention this, but this function can return null if the operating system cannot service the allocation.
Mm-hmm.
Okay? It won't crash the application right then and there. It'll just return null if it can't service the allocation. And then it's up to you to deal with it. Now, a lot of programmers, including myself, I'll admit, optimistically assume that that doesn't happen and just allow the application to crash when it tries to access that memory later on. Because, again, if it's returning null, it's pointing to a page that the operating system is probably protected, and so therefore trying to access that page will cause the application to crash.
Okay, and one last question on this slide. In Linux kernel, do we have, does system say the maximum amount of memory that you can allocate is like 500 megabytes, or we can go as high as we actually have as we have RAM on this box?
There's a lot of complications that come into that, like especially when you get into virtual address systems, which I'm sure that this class is going to go over later on. You know, virtual address space, I'm sorry, not system, virtual address space, the VAS. So that's a really hard question to answer. You know, it's going to vary by operating system, versions of operating systems. It's going to vary on whether or not you have a 32-bit processor or a 64-bit processor. I mean, so many things are going to play into what that maximum size is. I mean, I really can't give you a concrete answer what that maximum size is. Yes. I think that, you know, Jose has made a really good point on Slack there that with all these, you know, if you want to know more about any of these functions, you know, in Linux you can say man space, malloc, man space, you know, stir copy, man space, anything, and it will tell you a lot more about the function. So if you're unsure about certain things about these functions or what they return or under what cases they return, the return is the really big one. I'm not going to go over any of the socket programming stuff, but I will say this. The socket stuff can return weird stuff under weird situations. And so read the man pages about what they return and under what cases they return what, because if you don't have that fully qualified in your head under what circumstances it will return what things, you will run into trapdoors that will cause you all sorts of tragedy. So, you know, read the man pages on all the socket functions, understand what the socket functions can return and under what conditions they return those things. I cannot stress that enough. So that was a very good point. Do you have any other questions about memory management before I go on, Dimitri? Because this is an important point. Memory management is one of those things where most other languages kind of put you into this veil of ignorance about memory management, and C++ is like, nope, we're going to take off all the training wheels, and memory management is 100% your responsibility all the time. So I want to make sure that you understand it.
I understood it, thanks, but maybe later down the line when we cover pointers, I will have some other questions.
Yeah. So scope. We'll talk about scope really quickly. So scope is started by a curly brace, what they call an opening curly brace, and is closed by a closing curly brace. Functions must have a scope, so you cannot make an unscoped function. For control functions like if, for, while, they are optional. However, I will advise you that you always use them. In fact, for my team at NVIDIA, it is part of our coding standards that you must use a scope on all ifs, on all whiles, on all fors, on everything, because otherwise it can lead into some ambiguities under certain situations. And so, you know, it's just a little bit more white space on your screen. It's just a little bit more typing. Give everything a scope. It makes things a lot easier. Now, one big difference between C and C++, and this is one of the things that, because I'm usually a C++ programmer, and having this taken away from me in C makes me such a sad panda, is you must declare all your variables at the top of the scope. And then you can actually start writing code. And then the first function or code that you write, you're no longer allowed to declare variables in that scope anymore. I really don't like this part of C. It's hyper annoying. The compiler will just error out on you about it, but especially because I'm so used to being able to declare variables wherever I want in Project 1 as I'm going through it. One of the major annoyances is I'll just write variables wherever I want to, and I'll hit compile, and it's like, you can't do that. And it's like, oh, goody, now I get to move all my variables to the top, all the declarations of my variables to the top.
So you can't do the usual thing like in C++ for int I
No.
equals it.
No.
Damn it.
I know. I know. Makes me such a sad panda. Out of all the, I mean, there's a lot of things I'm annoyed about of having the C++ niceness taken away from me. That's kind of the one that actually irks me the most, just simply because it's constantly reminded to me. Okay. Okay, so like I said, this slide, I'm going to move these slides around real quick, because like I said, these slides should be up. Like, where do I talk about arrays? Right there. So these two slides should be right there. Okay. So, and I'm going to go ahead and post these slides later. So unlike most other languages, where is this? Oh, goody. I've lost a slide. Okay. So I'll have to talk about this, and then I'll recreate the slide later on. Oh, no, this is right. Okay, yes. So if you most languages, you probably never ran into a pointer in your life, because in some way, shape, or form, the language has abstracted the concept of a pointer from you, whether you're talking about C#, whether you're talking about Java, JavaScript, Python, all of them. The concept of what a pointer is completely abstracted away from you. So the way that I like to describe a pointer is I like to think of it as like an entry in the index of a book. So in the index of a book, you have a word you might have a word for like function pointers in there, and it will say function pointers is at page 556. That's basically what a pointer is. Is that a pointer? You're saying that the value that you're looking for, it isn't here, but you can find it over there. That's what a pointer effectively does for you. Okay. So you can declare it, like I said, *x. So how do I get the address of something? Well, in C and C++, the way you do it is with this ampersand operator, which is typically referred to as the address of operator. And so what it does is it tells you the address of y. Okay, and so you can say ampersand y, and that will give you that. You can have pointers to pointers, pointers to pointers to pointers. Typically, you don't need these things, but you can have them if you want them, just FYI. We did not cover the dereference operator. So to go the other direction, so there's two ways once you have a pointer you can use them. One way is with the bracket operator, similar to an array. You can say x bracket 6 bracket. That will give you the 6. So remember when I was saying arrays and pointers are not exactly the same thing, but for most intents and purposes they are. This is one of those situations where they're pretty much the exact same thing. When you say bracket 6 bracket, you're looking at the 6th element that's pointed to it. So if you're pointing to an integer, the pointer points to the first integer, and then you can just keep going as long as you want in memory. And you can go infinitum. You can even overflow the system around if you wanted to. I've done that accidentally a couple of times. That's a fun bug. The other one is you can say star X. The star is referred to as the dereference operator. And so what that does is that basically gives you Y again, the value at Y. And you can even assign both of these. So if I said, this equals 5, and I can say star X equals 2, and star X is roughly equivalent to X angle bracket 0 angle bracket. Those are roughly the same thing. The other thing that you can do with pointers that I forgot to mention is you can do certain kinds of mathematical operations with them. So I think I should go over those. So if I add a number to a pointer, if I say like x plus 5, what that means is that it will give you another pointer that is 5 integers forward. Now I want to be very clear here. It is 5 integers forward, not 5 bytes forward. It moves forward or backwards, because you can also subtract the number by the size of the underlying type, integer, float, whatever. Okay? It's a very important thing to understand. And the reason why it's very important to understand is sometimes you really want to increment by bytes. And in order to do that, you need to first convert the pointer to something that is the size of 1 byte, like a char star, then increment it, then convert it back. Does that make sense?
Yep.
Okay. The other thing is you can take the difference of 2 pointers. So if you have 2 pointers and you want it, like you have pitter 1 minus pitter 2, this will give you the difference of 2 pointers. Again, the difference will be not in bytes, but in the number of those primitive objects. Okay? And most times that's actually what you want, right? Is if I have 2 pointers to integers, I want to know how many integers apart they are. I don't want to know how many bytes apart they are. So this thing is doing by default what you usually want to have happen.
I have a question. So in this example, if you have int y and then int star x equals ampersand y, and then I do star x equals 2, will I also change the value of y?
Absolutely.
Okay.
That's the whole point of pointers to a certain degree. That's a very good and astute question, by the way.
And also, could you please show, like in code, how would you move the pointer by bytes?
Sure. So let me go ahead and create a new slide because we're running out of room. So you want to do something like this. So we started with that X example. You want to say char star X. And if you're unsure about operator precedence, just add more parentheses. That's my rule. Right? So that's basically what you would do. Is you basically first cast it to a char, which we know is 1 byte in size, then allocate 5 to it, then cast it back to an integer. And now we've moved it 5 bytes forward, rather than if we just said plus 5, that would move it 5 integers forward, which is not, like I said, but usually, again, what you want is you want to be able to advance a pointer by its primitive size. You're usually not interested in advancing a pointer by byte size. It happens. I've had to do it enough times that, in C++, I actually have helper functions that do this for me automatically. So it comes up, but it's not something that's super common.
Okay, and also to clarify, so whenever I use pointers, I must be very careful not to go over the malloc for that pointer, right?
Yes.
I don't. Okay.
Or not necessarily just the malloc, because you can take a reference of something like this, and you can take a reference of a structure, you can take a reference of a lot of different things. Because you can take the reference of a lot of different things, for that reason, you're going to find that you just want to make sure you don't go over the size of whatever that thing is that you took a reference. So if you took the reference of a structure and the structure is 20 bytes, you don't want to go over the 20 bytes of that structure. Okay?
Okay. one more question, and it's more about memory management. In Linux, do we have some specific block type structures for the memory? So let's say if I want to write some values somewhere, right? I also have some kind of header of the memory block with some magic numbers. Does something like that exist in Linux?
What would you
terminal?
use it for? Let me ask that question. What would you be using this thing for?
Okay, so I'm not 100% sure, but the world that I am working at is networking operating system. So, and I know that we have that. So whenever you basically want to write something, you will allocate this memory, but I mean it's not like you will also have some kind of additional header, and then you will also need to make sure that this header is correct, and it also points to the next block in memory and to the previous block in memory.
Okay, so if you want to create like a linked list or something like that, I'm not going to go over how to create a linked list in C++. You can do it, like you can create a structure that has the data and it has a next pointer and a prep pointer, and then you have to manage those. I would highly recommend, like at that point, if you want to get in that level of detail of things, I mean, I can do another Q&A next time if we want to go over like some more advanced coding examples, like maybe a linked list. We could do a linked list or a doubly linked list. I could do some basic coding examples like that and walk through the code and walk through how it works. That actually is a really good idea for the next time. Is that maybe what I'll do is I just have people suggest some simple sample programs to have me write and to have me go over how they work. So maybe like a doubly linked list would be, because it sounds like what you're suggesting there is a doubly linked list.
Yep.
So that would be maybe a good data container for me to just program up and show you guys how it works and why it works. So we could definitely do something like that. I also was going to mention that, I forgot to say this, you can allocate from the stack. Now, its lifetime, this is very important, is until its scope is gone. Because it's from the stack, there are greater restrictions about how much you can allocate. Most threads get 8 megabytes of stack on Linux, if I remember correctly. So you can't allocate a ton of data this way, but you can allocate data this way. And the way you do it is you just say char data size, so like 4096. I just allocated 4K of data from the stack. And I can make another, and I can say char, I can make a pointer and just say equals data. And there's no conversion here because, like I said, it's this whole thing that arrays and pointers are not technically the same thing, but for the most part they are. Okay, and one of the ways, for the most part, they are is that I can just assign an array to a pointer without any kind of cast. Okay.
Mm-hmm.
So you know, yeah. I think that's that. I mean, I've definitely used both of these idioms in my project. So.
Okay, hold on for a second. So, why are you calling this stack if this is just?
Well, for one of the nice things from a performance standpoint about allocating from the stack is allocating from the stack is big O1. Like literally, in most processors, it is a subtraction operation. Like a single subtraction operation, and you have allocated off the stack. So if you're allocating something small off the stack, and you know it's small, you reason about its smallness, it's a great thing to do. It's super fast. The downside, like I said, is that it has a limited lifetime of scope. That's a big downside, depending on the context. Sometimes that's exactly what you want. So the really nice thing about it is because its lifetime is limited in scope, you don't have to free it. You know, there is no free, and you can't accidentally forget to free it. You know that it's going to be freed as soon as its scope is gone. So that's an advantage of it and a disadvantage, depending on the context of its use. But like I said, the other disadvantage is it can't get as big as a malloc. A malloc can get really, really, really big. Like I could ask for 128 megs of memory out of a malloc, and most operating systems would give it to me. If I ask for 128 megs of stack, most operating systems will crash. So that's another disadvantage. It's like I said, a lot of it boils. The thing with a lot of flexibility means that you're given a lot of tools that do the same thing in different ways, and then it becomes up to you, the programmer, to figure out what the best way to do something is based off the context of what you're provided.
Okay. So in this particular case, when we're using stack, we also need to have a way to control how many values we already put on the stack, right?
The operating system takes care of all that for you. What typically the operating system does is it puts it allocates all the memory for the stack, and then it allocates another page that's read restricted, and then if you try to read and write into that page after the stack, your application blows up.
Okay, in these examples that you have on the screen, we will be using this portion of the stack, which is 4K bytes, just for a single variable per se, right?
Yes.
And then if you want to have another one, then you will allocate another one like that, right?
Yes, and
okay.
the good thing is that the compiler handles all of the allocation of all of these things so that you know that they're not overlapping. Okay? Then, like I said, the only rule is that when the scope goes away, you lose all that memory.
Is there a way actually to have a stack which is kind of like a shared stack for the program or something like that, where it's one? What?
Well, so in the case of the server, once we get to the pthreads, you can kind of do it in the sense that, if you know that the stack over here is never going to go away, the server stack is never going to go away, and you give a pointer to your client threads, they can use that pointer. I would recommend not doing that. You can do it. I would recommend you don't.
Okay.
It's a bad idea. But what you can do, and what I often do, is that I will allocate in a function some stack, and then I'll call another function from that function and provide that stack to the other function to fill out some data. And the reason is that I might want to change how much data between different invocations of that function it's filling out. Does that make sense?
Yep.
So
yeah, I'm asking all of these questions because, I mean, I saw it multiple times, and I mean, there are a lot of specifics how, networking operating system works, and so that's why I have this kind of strange questions about memory allocation.
Memory allocation is one of those things where it's it takes a long time to really understand it. It's a very long time, and really, I didn't really understand it very really well until I started writing my own memory allocators. I started writing my own versions of malloc, and when you start writing your own versions of malloc, then you really start to understand these things. But until you go through the pain at least one time of writing a malloc function and what a malloc function means, that it's a black box, and there's always going to be some things that are a little bit vague. Hopefully in the lectures, she'll at least go over some of the basics of how that works. So let's keep trucking. So let's talk about structures for a second here. So structures are a way to create a set of data that you can represent and pass around between functions and things like that. So you can, for example, create a structure like this. You can say struct my struct int xy float ab. It now is a structure that has all this data inside of it. Now, if I want to create an instantiation or variable of that structure, I have to say struct my struct Bob. Note the prefix of struct. You have to have that prefix in there. I'll go over a way in a second of how to avoid that prefix, but in general, you need that prefix. Now, the way you access a member is with the dot operator. So I'll say a dot bob dot a equals 5.0. Now, talk a little bit about this some more. So, like I said before, you can avoid the struct prefix by creating a typedef. You can say like typedef struct mystruct s. So what typedef does is that whatever this is, I'm creating an alias of all this called s. That's what typedef does. It creates an alias. For all intents and purposes, s is just the struct mystruct. It's as if you type struct mystruct. So I can say s, which is just the shorthand for struct mystruct, Bob. You can also do this. You can say typedef struct mystruct mystruct. And that will allow you to now say mystruct without it. You'll actually notice inside the Project 1 header files that the TAs did this. So there's that. So accessing members of a pointer rather than of a regular structure requires the arrow operator. So here I'm taking the address of Bob and creating a pointer to the structure. And now I'm accessing B through the pointer. And note the arrow. I want to make a point here that I forgot to mention about I'm going to go over functions here in a second. So if I don't mention this in functions, I'm going to mention it. So remind me about that. So let's go on to functions unless you have any questions about structures.
Yeah, before we move forward. So if I use it without pointer, right? So I just will say bob.a equals something. If I use pointer, I just replace dot with an arrow, right?
Correct.
Or I can do star pbob dot.
Yes, you can, and that's a very astute point. I did not mention that, and yes, you can.
Okay.
I think there's an operator precedent syntax where you have to say star pbob dot d rather than star pbob dot d. Like it has to be in the parentheses, is what I'm trying to say. But you make a very astute point that by combining those two operations together, you get that idiom. All right. So let's talk a little bit about functions. Functions typically have the following form. Type function, type 1, parameter 1, type 2, parameter 2, etc. The parameter is technically optional. If you're not going to use the parameter inside the function, you can omit it. If you set your warning and your warning is error levels really high, where the compiler will complain about the fact that a variable isn't being used in a function, sometimes you have to do this. But you know, usually you'll specify out the names of the parameters. I'm just mentioning that you don't have to. The first type is the return type. And you can only return one thing. We'll get into how you return more than one thing here in a second. But by the keyword return, you can only return one thing. This is unlike, say, a language like Python that you're familiar with, where you can return a tuple of things. You cannot return a tuple of things in C. You get to return one thing and one thing only. If you don't want to return anything, you can use void as the type. So you have to specify a type, but if you don't want to return anything, you can use void, and then actually the return keyword isn't even required if a compiler is aggressive enough to actually complain about you forgetting to use return, which, by the way, the compiler settings that our TAs have set up is that aggressive. And like I said, I am very happy with our TAs and the level of aggression that they've set to the compiler settings. Because you can make the compiler very lax and let you get away with a lot of nonsense, and our guys haven't done that. So let's just go ahead.
Yeah. So in case I actually want to return a couple of values, I have to create like a pointer or array or something like that and return
pointer, because you cannot pass. I want to make this very clear. Technically, by syntax, you can do this. Don't ever do this. Because what happens to an array when it's passed to a function, bad things happen to an array, bad things that you don't expect. So just only use pointers, okay? But you're absolutely correct. What you would do is you would create a bunch of pointers, and then you would just take the references of them in the calling function. Okay.
Okay. No, I was hold on. I was asking about not passing parameters to the function, but rather than returning.
Well, no, right. That's what I'm saying. By to return
Okay.
them, you would add them as additional parameters to the function. So they would be parameters here, like normal parameters, but they would be pointers. And then in the calling function, the function that's calling your function that wants to return multiple things, you have to take the address of those things so that when the callee knows where those addresses are, so it can dereference them and write to the original values.
Okay.
Because and the reason is that all of these parameters become copies. So if I say int x here, and then inside this function I set x to 5, the calling function's x will still be whatever value it was, because this function gets a copy. Okay? And this is another key point I want to make, because I don't think I made it in the slides. Never pass a structure without a pointer. And the reason why is if you pass a structure without a pointer, because everything's a copy, it will copy the entire structure. So if you have a structure that's like, 10K structure, this big structure, and you don't pass it by pointer, it will copy the entire 10K structure every time you call the function. That can get expensive.
Okay, but I also, if I am passing via the pointer, I have to be more careful, right? Because I can easily mutate the structure, right?
Correct. You can definitely change the structure. All right. Sorry, my daughter just woke up from her nap, and apparently she's not happy about it. My wife's taking care of it, though. Okay. So here's an example of a very simple function that just adds two values together. I do want to make note of this for declaration here. And this for declaration is basically what you'll find inside of a header file like this. So basically, this is just saying that a function exists in the universe called add, and it takes in two integers, and it returns an integer. Now, I also want to mention something. You cannot name a function the same name in C. You can do this in C++, and there are rules in which you can do this in C++. But in C, there can only be one function that is named add in the entire program. Okay? There is one other thing that you can do. You can add the keyword static in front of it. Static means it will not export outside of the compiling module, this file that you're compiling. So you could theoretically have multiple versions or incantations of add that are all static. But in general, just understand that C only allows you to have one version of a function named a particular way anywhere.
So we don't have function overload?
No, you do not. Not in C. Not in C. In C++,
No.
you do.
Okay, so basically, I will have to create a new name for the C function if there are 3 parameters right now, yeah?
Yes. If you want a version that has 2 or 3, you either have to create, or you just have to make it so that you have to type in those parameters. Because also in C++, you can create defaults. So like if you don't include a parameter, you can say, oh, if you don't include parameter, the last parameter, its value is this. In C, you can't do that either. So you have to specify out all the parameters.
Okay, so this is set panda number 2, yeah?
Yeah.
Okay.
Yeah. Well, this is what I mean. This is why at my company we use C++ and we don't use C. There are advantages of C. C, it's easier. C++, one of the biggest disadvantages of C++ is you can run into situations in C++ where it becomes difficult to reason about what the code is exactly doing because it can do things that you're not expecting. Whereas in C, what's really nice about C is there are no circumstances in C where something's hidden. Like in C++, you can overload an operator. So something really innocent looking like a plus can end up doing all of this code, whereas in C++, that can never happen. The unit of work of the plus operator is self-contained and very well understood. And so for operating system code especially, I definitely think that there's a reason why most people choose C over C++ in operating system code, because it's very easy to reason about what exactly the code is doing and cannot do anything more or anything less. But like I said, for the games that we develop at my company, we use C++, despite all that, because we're not writing an operating system, we're writing a game. So so I was talking a little bit about this, about how changing parameters will not be observed by callers. Okay, yep, and here's actually just a downright example of if you want to return a value by a parameter. There's a concrete example of it. Okay, and like you said, you have to be very careful when you're using this pattern, because you can modify the contents of the structure accidentally if you're not careful. And no, C does not support the const keyword that's in C++, so you cannot prevent someone from modifying the data. Sorry.
Okay, just to clarify, so whenever I pass variable via pointer, right? So I use star in the function declaration.
Yes.
But then later down the line, if I want to use it, I also use star, right? Well, if I want to dereference it.
Yeah, if I want to the dereference operator is star, yes. And a lot of times it's really good habit to go ahead and say if param not equal null here, or have some kind of check that it's not null. Especially if you want some return parameters to be optional, like a function may or may not want to know a particular return parameter, it can just pass null. Null is a pound defined at this point to be 0. It used to be pound defined to different things, but at this point it's always 0. So null basically means nothing. So you can use it as a hint. And you'll see in a lot of C++ code people checking if a pointer is null or not, and taking different paths of logic based off of the nullness of a pointer.
I have additional question. So in case we were talking about how expensive it is to copy structure, but I'm thinking right now, if my variable or my structure for some reason will be less than the size of the pointer, right? It would actually make sense.
Even close to the size of the pointer, absolutely. Typically, because the size of the pointer is either most operating systems that we're going to deal with for moving forward in the life of our lives are going to be 8-byte pointers. I really don't see the need for a 128-bit operating system anytime soon, because I think 64-bit systems can deal with in the petabyte range of address space. It's something ridiculous like that. So I really don't think that we're going to run into that roadblock again for a while. At least at the desktop application setting. It may occur at data warehouses where you can map other people's memory. But you make a very astute point. If it's small, it's okay. Like in NVIDIA, we make it a rule that we don't want to pass by value. Doing that is called pass by value when you don't make a pointer to it. It's called pass by value. We made a rule that we don't pass structures by value just to avoid the ambiguity. But one of the good things is we're operating in C++, and so oftentimes we'll put the const keyword in front of a lot of things so that we can't modify them. So, you're absolutely right, though.
Okay, thanks.
Yep. All right. Talk about function pointers, which is going to be the last, I think it's pretty much the last subject I'm really going to discuss today. And I'm going to probably say that this is both the most complicated subject that you're going to need to understand, and it's one that you're going to need to understand for Project 1, because if you look at the header file for the GF client, the GF server, they have function pointers in there, and they're expecting you to understand how to use those function pointers. So you need to understand function pointers. So we've talked a lot before about how C treats a pointer as just saying that there's something somewhere out there in memory. Well, function's no different. There's just memory somewhere that contains all the machine code for a function. Okay? And so and so when you give a function pointer, you're just saying the function exists at this location in memory. And this is extremely useful when you're writing library code. When you're writing code where you might want to call back into the person who's using your library's code, but you don't know what their code is doing. So a great example of this is the pthreads library. When you create a thread, you know, the pthreads operate, the guys who wrote the pthreads back in the 80s, I think, is when they wrote the POSIX pthreads. When they wrote that, they had no idea about all the different kinds of threads, billions, probably millions of different threads that all the programmers in the universe have ever written. And that's one of the really powerful things about function pointers, is that you can call into a function and you have no idea what that function does. It just has to follow rules. So let's talk about that. So there's two ways that you can define a function pointer. The first way is this. You can say int star, the star is mandatory, func pointer, int a, int b. What are we saying here? Well, what we're saying is we're going to create a variable called func pointer. So the variable is called func pointer that takes a function of the signature integer a, integer b. So it takes two integers as inputs and it returns two outputs. Now I'm going to give you the syntax of this is awkward. I hate the syntax of this. It drives me nuts. And I've been working with it for 25 years and I still hate the syntax. And I will never like the syntax. You can help the syntax a little bit by creating a type def. So you can say, go ahead and say type def int star function pointer underscore t, int a, int b. And then now I have an alias of that function pointer called funcpitter t. And so then when I want to create a func pointer, I can just say funcpitter t, funcpitter, like I would normally expect to be able to do with a variable. But again, you still have this type def that's really awkward. So you really haven't gotten rid of the awkwardness. So regardless, the syntax is bad. In C++, the syntax for function pointers or classes actually, if it's even possible to imagine, got worse. And it wasn't truly cured until C++ 11, which only came out 6 years ago, which is amazing. This is amazing to me.
Can you show what is the syntax in C++ 11?
It's good. Well, you can look up something called std function. So there's this thing called the std library, and they added something called function. And std function, and they also added lambdas, which coming from Python, you're aware of lambdas. The addition of those two things, the lambda syntax in C++ and std function, are what really, those were game changers in C++ in my mind. But they were additions to C++, not to C, okay? But big game changers. So let's go over a concrete example of how we might create a very simple operator. So let's say I wanted to get an operator based off of the character of an operation, okay? So I create a bunch of function pointers, addition, subtraction, or a bunch of functions, addition, subtraction, multiplication, division, that do exactly what you would expect them to do. And then I have a function called getOperator that switches on C and then returns addition, subtraction, multiplication, and division. Now you might have noticed this one little weird thing that I'm doing here. I'm doing there's a couple of weird things about this line that I want to go over that are just kind of like programming style that I tend to do. So one thing is in C, there's this thing called assert. What this does is in non-release builds, whatever you want to define a release build, debug build, which I think all our builds are by default debug builds. If this evaluation doesn't return true, it will crash the application telling you where it crashed and why. So it's a nice way to verify that under no circumstances should I be able to pass anything but these values to this function. And I want to know if I pass anything but these values to this function. So I've done this. I've also added this ampersand logical and with a string, just so that I have some sort of textual description of it. It's not required, but it's nice to have. Okay, so that's what this assert thing does. And then I fall through so that if it is built on a release build and this assert goes away, because that's what happens to asserts in release builds, it's as if they never existed, then at least it does something meaningful. i.e. it'll return an ad. You know, it may not be what I wanted, but at least it won't crash. So that's that. So how would we call one of these mythical function pointers? Well, here's an example right here. I can go ahead and get I can use the get operator function that I created up above, and I can get the subtraction operator. I can say, you know, 5 minus 2 using the function pointer, and that will return 3. Now, so you'll notice I dereferenced the operator and I put it in brackets like that. Okay. You can also call it like a regular function. However, I suggest you don't do that. And the only reason why I suggest you don't do that is by using the other syntax. You're expressly stating in your code that you're calling a function pointer. And that's a nice thing to have. Because function pointers, they're not exactly the same as function calls. They're a little slower. The compiler can't optimize them the same way. And you can, if you point a function pointer to a function that has a different function signature, or a function, or in the memory that's not a function at all, bad things can happen. Very bad things can happen. I think one of your fellow students was asking me a question a while back where he was looking at some code, not related to this course, but he was looking at some code where somebody was calling a function pointer to a function of a different function signature, and all sorts of strange things were happening as a result, and that's a very bad thing to do. So it's nice.
It was me.
Oh, it was you. Okay.
Yeah.
And so that's why I like to be very explicit here, using this syntax rather than this syntax. Okay. So, do you have any questions about function pointers? Or you asked a lot of really insightful questions on Slack when you're first asking about it. But do you have any more?
No. Right now I'm fine. Until I implement them in my program, I'm good.
Well, that's why this review is important, because this review is just review, and then, like you said, it's all great until you actually try to code it, and you're like, wait, how does this work? So I'll just talk about a couple of basic string functions since you're going to need them. So you have to include the string library. There's more functions in there, like stircat, stir reverse. There's all sorts of string functions. Feel free to look at all the string functions, but I'll just give you some of the nicer ones that you'll definitely need. String length returns the length of the string, not including the null terminator. Very important. It does not include the null terminator. Stir copy copies two strings. This function does not respect how much space destination has at all. And so it is extremely dangerous. As a matter of fact, I would say under no circumstances should you call stir copy. Okay? Under no circumstances call stir copy. It's part of the reason why I bring it up. As a matter of fact, don't call its cousin stircat, which strcat, string concatenate, which does concatenation. It also does not respect the size of destination. These are evil, evil, evil things. strncat's not much better because it does weird things too. So usually I end up creating my own versions of these functions that are a little bit more sane. Because, for example, strncopy copies no more than the size bytes from source to dest. However, if source cannot fit in dest, dest will not be null terminated. And so normally I'll end up creating a function called like safe stir copy that takes the dest, the source, and the size, and then also guarantees that it will always be null terminated. The string libraries. Part of the problem is that these string libraries were written in the 70s, I think, long time ago, and we didn't know as much things about like how these things can go wrong back then. We've learned a lot of lessons. A couple of resources for you. The Linux man pages are extremely important. If you're wanting to know more about how any of these functions work, the return codes, especially the return codes of sockets, highly recommend this stuff. And then I mentioned this, See How to Program by Dettel and Dettel. Extremely valuable book. If you were to see the version of my book on my bookshelf back there, you would see that the binding's falling apart and stuff like that because I've referenced it so many times. I do want to mention any edition will do. So I checked on half.com, and there are editions that you can get like the second edition, which is the edition I have, for like $0.25. So if you're looking for a good C book, get the Dettel and Dettel book off of half.com for a couple of bucks. and plus shipping and handling, and then you'll have a good C book to deal with to help you along. Because the thing that I really like about Dettle goes into a lot of detail, but at the end of every chapter it has a lot of exercises as well that are of ramping difficulty. And so if you want to challenge yourself to try to figure out how to do something, you can do these example problems at the end. And then I'm sure that if you were to ask questions like, hey, I tried this example problem in the Dettle book and I can't figure it out, I'm sure that somebody on there would be more than happy to help you figure it out or even help you code it so that you can understand how to do it.
Do you recommend the famous C programming language by Kernighan Ritchie?
If I know what the book is, see, let me pull it up real quick. See? I don't know which book you're talking about. Oh, this book. This book is really for advanced programmers.
Okay.
It's a great book if you're good at C. Like if you're not just good, but you're great at C. It will make you even greater. It is not a book I recommend at all for someone who is trying to learn the language.
Okay.
It dumps you right into the deep end and expects you to be able to swim, and that's not necessarily a good thing. So, you know. All right.
Okay, Chris. I really appreciate the time that you spent here with me. It was really helpful.
No problem. And if anybody wants more, please let me know, because I'll be more than happy to set up some more of these. I'll try next time to keep it down to an hour, but I figured for the first one, I might as well just go over all the slides I have.
Thank you very much, Chris.
Bye.
Bye. Cheers.